Hi, my name is Sam Dekbar, and this is my lab for Physics 2211, Lab 5, Choose Your Own Adventure. The purpose of this lab is to investigate and compare the motion of an object sliding down ramps of various degree angles from the ground. The fundamental physical principle we will be studying in this lab is Newton's second law, or the momentum principle, which states that the acceleration of an object is dependent upon the net force acting upon the object and the object's mass. Our result preview is that as the angle of the ramp increases, acceleration increases. However, we do not include friction in our computational model, thus the acceleration of the marker falling down the frictionless ramp is equal to 0. In reality, friction force acts parallel to the ramp surface in the opposite direction of the motion of the marker. On the left here, we see the applicable models to our lab, the 3 ramp angles degrees we will be testing, and how we can break down these into vectors, namely that of the gravity force into its x and y components. The force in the y direction equals mg cosine theta, and the force in the x direction equals mg sine theta. On the right, we see the important equations that we will be using in our code. dp dt equals f net, final position equals initial position, plus average velocity times delta t, and final velocity equals initial velocity plus net force divided by mass times the change in time. Now for the experiment. The system is the object sliding down the ramp, which in this case is a marker. The surroundings is everything else. Our procedure is to edit the computational model from Lab 1 to account for the net force acting on the marker as it slides down the ramp. In Lab 1, when we were rolling the marker along the meter stick with a constant velocity, the net force was 0 newtons. Then we repeat the steps for 3 different angle degrees of 30, 45, and 60. I've included their equivalent measurements in terms of radians. Then we compare results and analyze how the angle of the ramp affects the motion of the marker. Our key assumption in this lab is that there is no friction force acting on the object. The ramp is smooth enough to neglect this force. Here are the initial conditions and system properties for our ClosScript code. The marker mass is 1 kilogram, the original position is 0 meters, and the original velocity is 0.256 meters per second. Also, the time is 0. Here, you can see the equations from earlier implemented into our code, where above we calculate the net force. Secondly, we apply the momentum principle, which is our fundamental physical principle. Here's a better look of how we added the equations into our code based off the given equations and our variables in ClosScript. Here's how we edit the net force equations for the 3 different angles to simulate the different degree angles between the ramp and the ground. Notice how we break up the net force into x, y, and z components separately based off the model we viewed earlier. Therefore, the resulting net force calculated here in our ClosScript code will be a vector. Here are the resulting computational models for the degree angles between the ramp and the ground of 30 degrees, 45 degrees, and 60 degrees respectively. As you can see, all these graphs are the same. The axes on this graph represent position versus time, meaning that the motion of the marker sliding down the ramp is the same regardless of the angle between the ramp and the ground. Here is the shared velocity versus time graph between the 3 angles of the ramp, and as you can see, the marker moves down the ramp, velocity is not constant. This negative velocity slope means that the object is slowing down over time. Finally, for our analysis, our conclusion from this lab is that the motion of the marker or any object sliding down the ramp is the same for all angles of the ramp between the ground, given all the other variables are held constant. One possible source of error in our data is not including the friction force acting upon the marker sliding down the ramp. Now for a couple what-if scenarios for deeper understanding. What if the ramp made a 90-degree angle with the ground? Then the marker would act as a free-falling object, as we saw in Physics Lab 2, and the acceleration would be at its maximum. What if the ramp was longer? Then the time it takes for the marker to reach the bottom of the ramp would be much longer. That's all. Thank you for watching my presentation.